Recall that for a population to be in Hardy-Weinberg equilibrium, for it to have unchanging or fixed allele frequencies, all five of the following assumptions must be met. There can be no natural selection, no genetic mutation, no gene flow, no migration. It has to be a large population, and there has to be random mating. If any of these assumptions are violated or not met, then allele frequencies will change and the population will evolve. So there are any number of real world examples of these assumptions being violated and the population then evolving. But here's just one. This is the real world diversification of a group of frogs known as African reed frogs. You can see the phylogenetic tree here for this clade of frogs, but they've diversified as differing color dimorphisms, sexual dimorphisms. So differences in the phenotype between the sex affects mate choice. And when that happens, it violates both the random mating assumption as well as the no natural selection assumption, because some frogs, because of the colors that they happen to display, are going to be more likely to pass along the genes, the alleles for those colors. So next, we're going to focus on what actually drives most evolutionary change. What causes allele frequencies to change from one generation to the next. Okay, the three major drivers that cause the majority of evolutionary change that you're going to be responsible for are genetic drift, gene flow, and of course, we know all about natural selection. Okay, so we remember our avian predators taking out the light colored rock pocket mice on dark lava flows. Here we see the opposite. One of my favorite owls, the largest species in North America. This is the great gray owl, and it is snatching a dark mouse on white snow. So when we think about natural selection, we're thinking about unequal rates of both survival and reproduction. But first, we're going to start with genetic drift.